Welcome to this video on suspension system modeling. The essential function of a suspension is to connect the vehicle body with the wheels. Thereby it's possible to carry the body along the driveway and to transmit forces on the horizontal plane. In other words, transmit the propulsion force. The wheel suspension gives the wheel a vertical movement possibility. And as a result, the wheel follows an uneven road surface to a certain extent. By using springs and dampers in the suspension, the resulting body movement is reduced and driving safety and comfort are ensured. Our aim when modeling will be to describe how the road surface affects the wheel and body motion. The three-phase method will be applied when deriving the model. To simplify the problem a little bit, a common approach when studying a suspension system is to study only a quarter of the vehicle, a so-called quarter car model. A schematic drawing of the suspension system can look something like this. Two masses connected via a spring and a damper. The upper mass represents the vehicle body or the chassis, and the lower mass represents the wheel. The wheel is affected by the road surface via the tire, which can be represented as a spring. The schematic diagram gives you a feeling of how to divide the system into a block diagram. The input will be the road surface and the output will be the positions of the wheel and the chassis. As we are dealing with a mechanical system, it is suitable to create a free body diagram of the suspension. For the wheel, we have three forces acting on the system, except for the gravitational load. It is the tire force from the road and the forces from the suspension, the spring and damper force. For the chassis, we only have the forces from the suspension. We're now ready to go into the next phase in the modeling. Let's start with our conservation law. As we are dealing with a mechanical system and translational motion, a force balance will be a suitable conservation law. Newton's law, as you already know, states that the sum of the forces equal mass times acceleration. Looking at our free body diagram, we see that mass times the acceleration of the wheel equals the spring and damper force minus the tire force. And mass times the acceleration for the chassis is equal to minus the spring and damper force. We now have our conservation law. Let's continue to the constitutive relations. We know that the acceleration is the time derivative of the velocity, and the velocity is in turn the time derivative of the position, and this is valid for both the wheel and the chassis. The tire force, as the tire is represented by a spring, is given by Hooke's law, which states that the force is equal to a constant, the spring coefficients, times the elongation. The spring in the suspension is modeled in the same way. And for the damper, which is a friction element, the force is proportional to the velocity. So now we have a number of equations. And the next phase is to sort the equations and put them into the general state space form. The first step when forming the state space model is to select state variables. We see that we have four time derivatives: the position of the wheel and the chassis, and the velocity of the wheel and the chassis. So let's choose these as our state variables. Let's start forming the state space model by taking the derivative of the first state variable, the wheel position. The time derivative of the position is given by this equation. And if we put it into our equation, we see that the time derivative of the state variable is a function of one of our state variables, in this case the wheel velocity. Let's continue to the next state variable, which can be the wheel velocity. And we can continue by putting in the equations, one at a time, into our model, until we have all derivatives of our state variables as function of the state variables or the input signal. So in this case, the state space model of the suspension system will look something like this. We can, if we like, do a variable change, where x is the state variables, u is the input signal, the road surface, and y is the output signal. In this case, we have two outputs, the wheel position and the chassis position. With this name change, the model can be rewritten as this. As this model is linear, we can rewrite it in matrix form. And doing this, we end up with the following representation. So, this is the model describing the quarter car suspension system. It should be noted that the input signal to our model is the road surface. So our design task could be to choose the damping and spring coefficients in the suspension so that we fulfill certain specification on the body movement. This is the passive suspension system control objective. For an active suspension, we need to add an actuator to our model controlling the suspension system. The road surface could then be seen as a disturbance to our system. Our design task is the same as before, to fulfill certain specification on the chassis movement, but now with the opportunity to use the actuator to further control the suspension. How the integration of the actuator model into the suspension system model will look like, I leave to you to figure out by solving the exercises following this video. Thank you for watching and good luck with solving the exercises.